Alright, Mackey, so here we go. You wanted me to answer this question. So here's my your function. X to the fourth minus 2x squared plus 3. And you want to know when the function is increasing, decreasing, concave up, concave down, and where the inflection points are. So first thing we're going to do is find the derivative. And the derivative is 4x cubed minus 4x. And this is a function that we can graph and find the zeros really easily, not the original f of x. So I'm going to factor out a 4x. It's going to be x squared minus 1, which continues to factor to x minus 1 times x plus 1. So now I know the zeros of this, so I'm going to graph f prime of x. So the zeros are 0, 1, and negative 1. It's cubic and it's positive, so it's going to start down below, go straight through all these roots, and that thing looks like that. All I really care about is when it's negative or positive. And then you want to do a chart. I'll do it red for cardinal red. And so, because you were wondering about the charts, you could make a little chart here. Here's x, and here's what you know about f prime of x, and then right here I'll put in what that tells me about the function itself. So you can see that when x is between negative infinity and negative 1, my derivative is negative, which means that the function is decreasing for those values of x. And then at negative 1, the derivative is 0, so it could be a max or min, but we'll wait to see which one. And then from negative 1 to 0, my derivative is positive, so this is increasing. So if my function went from increasing, I'll put it right here, increasing to decreasing, you can see that it must be a maximum value. So at negative 1, that's a max value of the function. Then from at 0, it's 0, and we'll wait to fill that in. And from 0 to 1, it's negative, so this must be decreasing. So if my function f went from increasing and then had a horizontal tangent, because the derivative is 0, to decreasing, increasing to decreasing. Ooh, I just did that wrong. This would be, sorry, it's late. This is an eraser. I think I mean min here, right? If it goes from decreasing to increasing. I just did that wrong. Erase that too. Okay, we're going back here, Mac. Sorry. Decreasing to increasing is a minimum. And then increasing to decreasing, increasing to decreasing is a max. And then from at 1 we have a 0 again, and then from 1 to infinity, this thing, the derivative is positive, so it must be increasing again. So again, we must have decreasing to increasing a minimum value at 1. Okay, now I'm going to take the second derivative, and that's going to tell us about the concavity, and the second derivative is, let's see, the derivative of this one is 12x squared minus 4. That's an easy one too. So, did I do that right? Yeah. And we can factor out a 4, and that becomes 3x squared minus 1. So that function has, let's see, where are the zeros for that? 3x squared minus 1. 1 does that equal 0. When 3x equals 1, 3x squared equals 1. X squared is 1. So when x is plus or minus 1 over root 3, or root 3 over 3. So I'll now graph the second derivative. So here, I'm going to graph the second derivative. I'll do it in, how about a rainbow color there? Okay, so the second derivative has roots at root 3 over root 1 over root 3. So that number is less than 1. So somewhere there and there. and it's a quadratic, and it's going to go up. Looks like that. And these points are positive 1 over root 3, 0, and negative 1 over root 3, 0. Those are a little bit more than a half, both those numbers, by the way, negative half, so approximately 0.5-ish, 0, and negative 0.5-ish, 0. Okay, so now you need to, we're going to continue with this chart thing again, except now we're going to do it for the concavity. So I'm going to do it again, except this time I'm going to look at x, the second derivative, and what that tells me about the function. So from negative infinity until negative 1 over root 3, my second derivative is positive, so which means my function is concave up. And then at negative 1 root 3, the derivative, second derivative is 0, so it could be a point of inflection, but we're going to wait and see. And then from negative 1 over root 3 until 1 over root 3, the second derivative is negative, so it must be concave down, my function. And then from at 1 over root 3, we get a 0, so it could be a point of inflection, and then 1 over root 3 until infinity, it's positive, so it's concave up again. So both these are, if they change concavity, they must be inflection points. Okay, so now you pretty much have it all together, and if you want to, you can draw the graph of the original by following along. Ooh, that's not going to go up that well. Let's see if I can push, okay, oh, I can push this up, push this up. So if I want to graph the original thing, I just follow those original things, and I can see that must be decreasing and concave up. So to be decreasing and concave up. So it's going to be decreasing and concave up until negative 1, and we're going to have a minimum. Still going to be concave up until you get to negative 1 over root 3, so that would be kind of right there at that point. And then we're going to switch and be increasing, because we're increasing from negative 1 until 0. So I'm going to be increasing but concave down now. And then at 0 I'm going to be decreasing. And then again we're going to still be concave down until positive 1 over root 3. There's the other inflection point. Then I'm going to be concave up until 1. I'm still decreasing, and then I'm increasing the rest of the way. So that's what my function looks like just from looking at the first and second derivative. And that's it for that question. And then you asked me this question: if f of 1 is 10 and f prime of x is greater than or equal to 2 when x is bigger than 1 and less than 4, how small can f of 4 be? I'm going to change marker back to black. Well, if you just made a little picture and f of 1 down here is 10, like that, that point I know is on there. If the derivative is greater than 2, it means it's already positive, it means it's increasing. This function is always increasing. So if I start at 1 and then I go to 4, and I have to be increasing no matter what, and I can, who knows how much I could be concave up, could be concave down, but I'm still increasing, then this f of 4 needs to be greater than 10. So the smallest it can be is a little bit more than 10. And then you asked me one more question here, which I don't really know if I can answer this, but I'll try. So you said that prove that 2 x plus cos x equals 0 has one real root. Well, you know that the cosine of x has to be a number no matter what you put in between -1 and 1. So if you're, no matter what I put in for x, this number is between -1 and 1, then you have a line, something between -1 and 1, equaling 0, and if you have a line, there's one real root. That's about all I can say for that one. I'm not sure if that's perfect, but that's it. Alright, love you, buddy.